Brian Greene is here. He is a professor of physics and mathematics at Columbia University here in New York. He's also one of the most prominent minds behind one of the most important scientific advances of our time, the string theory. It is a theory which explains everything that constitutes our universe. Greene's best-selling book, The Elegant Universe, is now the basis for a new three-part NOVA series here on PBS. I am pleased to have Brian Greene back here on this program and sitting at this table. Welcome back.
Thank you.
Now, you need to explain to us what the string theory is.
Sure, happy to. The question that string theory tries to answer is one that really people have asked for thousands of years, which is, what is the basic, elemental, uncuttable constituent that makes up everything in the world around us? Wood, metal, chairs, tables, what at rock bottom are they made of? Now, you can think of it like, take an incredible microscope, zoom in on any piece of matter, and what will you ultimately see? Now, we know that you'll see atoms sooner or later if you go far enough down, but you can go further. They have electrons that orbit a nucleus, which has neutrons and protons, and if you crank up the magnification more, you would actually see quarks, little tiny particles inside of neutrons and protons. That's where the conventional theories stop. String theory says, crank up that microscope even further, really even further, and inside those particles you would see something else. It's a little filament of vibrating energy. It looks like a string. That's why we call it string theory. And the essential idea is that the strings vibrate in different ways and in that manner produce different particles. It's kind of like a string on a violin. It vibrates different ways and we hear different musical notes. In string theory, the little filaments vibrate different ways. We see them as different particles. So everything, if you will, is the music of these little strings.
Is this the majority opinion in the scientific community?
No, I don't think so. It's definitely much more accepted than it was 5 or 10 years ago.
So what's happened to make it more acceptable? More powerful computers or what?
No, I think it's really the theory has just developed in a manner and answered certain questions that couldn't be answered using previous techniques. One has to do with black holes. There are certain mysteries about black holes.
That's the universe, isn't it?
Well, the black holes are out there, we believe. There's real observational evidence that they're part and parcel of our universe. So you want to understand them as well as you can. And before string theory, there were ideas about black holes that nobody could establish, having to do with how much disorder, or the word is entropy, they have. String theory has resolved this issue. So I think many have come to the conclusion that, although we don't know whether it's right or wrong, and we won't until we have experimental evidence, that really is the arbiter, but has had such progress and made such strides that it needs to be taken very seriously.
Okay, to repeat myself in a different way, the answer to the question is string theory. What's the question?
Well, the question number one is, what are the basic elements of the universe? The fundamental ingredients?
The basic fundamental elements of the universe.
That's right.
Okay, what else?
And the second question is, how do we find a unified theory? That was Einstein's dream, to find, if you will, a single equation, a single principle that would describe everything. And he struggled to find this unified theory, and he failed. And we think string theory is the unified theory.
What's the alternative? I mean, what's in competition for a unified theory?
There really isn't, at this moment, competition.
The theory of everything,
and I should say that that's part of why people are enthusiastic about this theory as well. It's, in a sense, the only real game in town, if you want to find one theory that can describe everything. You see, before string theory, there were two theories. Einstein's theory of gravity on the one hand, quantum mechanics on the other.
Right.
Gravity is for big things, quantum mechanics is for small things. The problem was putting them together was very difficult. No one was able to do it. They conflicted with each other. String theory comes along, shows how to put them in one package. It all works.
If Einstein was the greatest physicist or mathematician of the 20th century, who is the greatest physicist or mathematician of the 21st century?
I think it's hard to say. It's still a little early.
Well, 3 years.
But if I was to say who's the greatest string theorist, that's a question I think many of us can agree on, which is Edward Witten.
Yeah, now he's involved in this, right?
Oh, he is the leading string theorist in the world. He's really driven the subject in a variety of different critical ways.
So your claim to fame is that you are the first guy to popularize the string theory.
Well, that's one thing. I hope it's not the only thing, because I am a scientist
I
at
understand
heart.
that. I mean,
But yeah, definitely.
But I mean, you were out there, and then you've got Nova investing $3.5 million to do this series of things. And
that's right. Yeah, you know, I felt that these ideas are so interesting, and they touch on questions that are so close to the hearts of so many people. You know, where did the universe come from? What is space? What is time? What is this place? And the problem has been that the developments which have made progress on these questions are usually phrased in the language of mathematics. Most people don't speak mathematics. So the point of my book was to...
we can all be happy about that.
Yeah, well, the point of the book was to, you know, peel away the mathematics. The point of the NOVA program is also peel away the mathematics, show these things visually. In a sense, take a handbook...
But we can't see the filaments.
Well, that's the thing. If you took a real camera and tried to see the filaments, you couldn't do it. So what do? We do what Hollywood does.
A little animation here?
We use animation. So rather than trying to animate The Matrix or trying to animate Star Wars, why not animate real science as we currently think about it? And that was the point of the program.
So you went out and got some fancy animators and you showed them said, look, how do we explain filament? And that's what they did.
That's what they did.
All right, take a look at this. This is a clip from NOVA. This 3-hour NOVA presentation of the Elegant Universe premiered on October 28th, and it continues on Tuesday, November 4th at 8 p.m. So if you missed the first, see the second, November 4th at 8 p.m. right here on PBS. Roll tape.
This Manhattan universe fits with an old classical vision of space. Basically, a flat grid that's static and unchanging. But when Albert Einstein looked at the fabric of space, he saw something completely different. He said that space wasn't static. It could warp and stretch. And there could even be unusual structures of space, called wormholes. A wormhole is a bridge or a tunnel that can link distant regions of space. In effect, a cosmic shortcut. In this kind of universe, my commute would be a New Yorker's dream. But there's a hitch. To create a wormhole, you've got to rip or tear a hole in the fabric of space.
What's the most powerful argument against this?
Against string theory, the most powerful argument is that it has not made a testable prediction. The usual way of thinking about science is you come up with ideas.
Well, that's an agnostic idea, isn't it? But it's not an idea against it.
Well,
maybe so. If you know you can't test it, you can't.
Yeah, if you were to go to most physics departments and find the anti-string theorist, I think the argument they'd give you would be nice ideas, but they haven't been tested. So it's not physics, it's philosophy, or it's theology. It's not what we call science. And I think the best answer to that is this is a work in progress. And we are getting closer, I believe, to having testable predictions. So we have to wait and see.
I love the idea of a theory of everything.
Yeah.
Thank you.
Thank you.
Great to see you again.
Good to see you again.
Thank you for joining us. See you next time. Let me remind you, NOVA, here on PBS, Tuesday, November 4th at 8 p.m. You can catch up with the story there and be taken into the future. See you next time.